Welcome to The Explainer. Today we're diving into some seriously cool stuff, threshold cryptography. It's this fascinating idea that tackles one of the biggest risks in our digital world, what happens when a single secret key just holds way too much power. This concept, well, it fundamentally changes how we think about protecting our most valuable information.
So let's kick things off with this one. Really big question. Our entire digital lives are built on keys, passwords, all kinds of secrets. But what happens when the security of an entire company, or maybe your life savings, rests on just one of them? That right there is a single point of failure, and it's a huge problem.
So traditionally, you've got one person or one server or one device holding this all-powerful secret key. If that key gets lost or, stolen by a hacker, or maybe even compromised by a rogue insider, boom, everything it protects is suddenly completely vulnerable.
Okay, so how do we solve this? Well, the core idea behind threshold cryptography is actually beautiful in its simplicity. Instead of trying to guard one super powerful key, what if we just split it into pieces? Let's take a look at how that actually works.
The mathematical intuition here is surprisingly simple, really. Think back to your old geometry class. One single point in a graph, it tells you basically nothing about a line. But give me 2 points, and I can draw exactly one line through them. Now imagine that line is the secret. To bring it back into existence, you don't need every piece of information in the universe. You just need a certain number of those points, a threshold.
So there's this protocol called Shamir's secret sharing, and it formalizes this whole idea. You've got a central dealer who takes a secret and kind of encodes it onto a special mathematical curve. Then, the dealer gives each person in a group a single unique point from that curve. We call that their share. Now, no single share reveals what the secret curve is, but get enough of those shares together and you can reconstruct it perfectly.
But, here's the catch, and it's a big one. We've just moved the problem, not solved it. We got rid of the risk of having a single key holder, sure, but we've just created a new risk. A single, all-powerful dealer who makes all the shares. What if that dealer is malicious? Or what if they get hacked? We're right back where we started, with a single point of failure.
So, the real challenge, the crucial point, is this. How can a group create secret shares together without a central dealer who knows the full secret? The answer is in the math, and it all starts with something that sounds simple but is, believe me, incredibly hard to get right. True randomness.
Yeah, you might be surprised just how easy it is to completely mess this up with some very, very dangerous consequences.
Let's say you're a developer, right? You might think, oh, I'll just use a basic random number function from a standard library, something like math/rand in the Go programming language. Seems easy enough.
But here's the trap. The documentation for the code literally tells you not to do this for security. This kind of randomness, it's just not secure enough for cryptography. It's for stuff like video games, not protecting secrets. An attacker could potentially figure out the pattern, predict the so-called random numbers, and poof, your secret is gone.
Okay, so what if we get a bit smarter? We use a real cryptographically secure source of randomness. That gives us a random byte, a number from 0 to 255. But let's say we need a number in a smaller range, like, less than 107. The obvious move is to use a modulo operation to shrink it down. Seems clever, doesn't it?
But this introduces this really subtle and very dangerous flaw. It's called modulo bias. See, because 256 is not perfectly divisible by 107, the numbers at the beginning of the range, in this case from 0 to 41, they're going to show up just a little bit more often. And that tiny, predictable bias, that's an open door for an attacker. For real security, randomness has to be perfectly uniform.
And this brings us to the real solution, distributed key generation, or DKG. These protocols use some really clever cryptography to let a group create a shared secret collectively. Think of it like everybody running their own little secret sharing process and then combining the results, all while checking each other's work along the way. And the result? No dealer. No single point of failure, just trust that is truly distributed.
So, the group has generated these secret shares, and they did it without a dealer. That's great. But this now builds to something truly amazing. How can they use those shares to do something useful, like sign a document, without ever actually putting the full secret key back together?
This is possible thanks to a special type of signature scheme called BLS.
What's important here are three key properties. BLS signatures are small, they're consistent, and this is the crucial part, they can be added together. They're aggregatable. And that last property, that's the magic ingredient right there.
Okay, so BLS verification relies on some pretty advanced math with a property called bilinearity. You're going to see an equation on the screen, but don't worry, you don't need to be a mathematician to get the point. This equation is like a magic check. It allows anyone in the world to use public information to verify that a signature is valid for a given message, all without ever seeing the secret key. And here is the final, absolutely mind-blowing part. With BLS, each secret share that a person holds, it acts like its own little miniature secret key. So when the group needs to sign something, each person creates what's called a partial signature with their share. Then you just add all those partial signatures together and they form one final, totally valid signature. The master secret key is never reconstructed. It never exists in one place, ever.
So, what can we actually do with this powerful new tool? Well, the applications give us a real glimpse into a much more secure, resilient, and decentralized future.
Let's just take a powerful, real-world example. You could split the key to your Bitcoin wallet into, say, 5 shares. You give one to your spouse, one to your lawyer, and one to each of your 3 kids. Then you could set a rule that any 3 of them can combine their shares to get access to the funds. You've just created a dead man switch or a really robust inheritance plan without giving any single person total control.
And the potential goes so much further than that. I mean, imagine building more secure electronic voting systems or truly fair sealed bid auctions where nobody can peek at the bids. In finance, it can help prevent certain kinds of market manipulation. It can even allow for social recovery, where your trusted friends can help you get back into an account you're locked out of, or creating digital documents that only unlock after a specific date. Each one of these is a fundamental building block for a more trustworthy digital world.